Good afternoon, everyone. We're going to start today doing this problem in the book. And this problem is saying that we have a steady, incompressible parallel laminar flow of a viscous fluid falling between these two infinite vertical walls. The distance between the wall is h, and the gravity acts in the negative z direction. There is no applied force or pressure driving the flow. The fluid is only falling by gravity. The pressure is constant here everywhere in the flow field, so we're not going to here discuss the pressure field, and we're just going to calculate the velocity field and sketch the velocity profile at the inlet and at the outlet. But here the pipe won't look like this, which has the same cross-sectional area throughout the entire pipe. We're going to actually vary it and make it more complicated, which is we're going to have a cross-section, a pipe with a different cross-sectional area that has a high cross-section area in the beginning, and at the low and at the end it's going to have also a very high cross-sectional area, and at the middle it's going to have a very short cross-section area, so it's going to converge in the middle. And the diameter in the beginning is the same as the diameter at the end.
Well, probably we are going to do a 2D analysis. So first we are going to go here and we're going to edit the properties so it can only do analysis in the 2D direction. After that, you go into the community and we use the design modeler to create a new geometry. Now we wait, geometry activates. Yes. Now we only need to create geometry in the XY plane, so we choose the XY plane, sketching. First we create a rectangle. Since our problem states that it has to be an infinite length, we're going to make a large difference between the diameter and the length. So first we're going to create a rectangle, and then we are going to modify its dimensions. It's going to be a 10-meter long length, and it's going to be 20 centimeter diameter. Now, in addition to having all of these problems, our shape is also going to be narrower in the middle. So in order to do this, create a new rectangle somewhere along the geometry. Now we also modify that dimension. Maybe 4 meters away. 2 meters length. Now, in order for it to narrow the middle, also draw a line each side. We'll also modify their dimensions as well. Which is going to be 0.5 meters. For both sides. Now after final diameter, we're going to specify the diameter, which is going to be 0.05. Since it's axisymmetrical, it's going to be equal on both sides. So we go to concept and we select surfaces from sketches. Now we select our surface, we click apply. Now we have selected our geometry. Then we click on generate. Now this tells ANSYS that this geometry is our surface, our pipe. After that, the solution is saved, and we move into creating the mesh. We wait for the program to start. Now our geometry is loaded into the mesh. Now we need to create the mesh. In order to create the mesh, first we go to mesh control and do face meshing. We select our surface and we click apply. This tells us along this is where will be our mesh. In addition to that, we will do face mesh sizing for the mesh. Sizing is important in order to allow us to determine how many divisions for the mesh do we require. Now we select in the type. We select now we select our edge, then we go and select 100. Now along this edge, we are going to have 100 divisions for the finite element. We do sizing for the opposite edge as well. However, the opposite edge's geometry is much more complicated. So first we need to select different geometries and apply different number of divisions for each. It's important to also maintain the number of divisions across both edges in order to have a uniform mesh. So the combined number of divisions for all these geometries should equal 100 as well. Now for these two we will use 30 divisions for each. Sizing again. We'll do 220 divisions for this one. And finally, sizing, we will choose 10 divisions for each. Alright. Now finally we go and we select the inlet and the outlet edges, and we do 5 divisions for each. Now we have specified the face meshing and edge meshing for each. However, this is not done. First, we also need to modify the behavior of the meshes. So we go to each mesh and we choose hard behaviors. After specifying that our meshes are all hard, we can generate our mesh. Now our mesh has been generated. As you can see, it's uniform. But this is not done. In order to make our job easier when we're setting up the problem, we will now specify the boundary conditions for the axes and the walls. First, we select this edge, and then we select create name selection, and then we say that this edge is the wall. Since our problem is axisymmetrical, this edge will be also on the other side. See? Now we have the wall. We do this again for other edges, like the axis, and of course the inlet and outlet.
We're going to start do the problem setup. Okay, and we're going to choose double precision for more accuracy, and we're going to check first on general. We're going to go to general. Okay, and we're going to select check, and it has to be axis symmetric. We're going to check whether the mesh is right or wrong. And we're going to choose display in order to see if all of the surfaces are selected. And then I'm going to close. Okay. Then I'm going to go to models, and I'm going to choose viscous laminar. Okay. And then I'm going to go to materials. In materials, I'm going to choose fluid. Okay, and I'm going to specify the density, which is equal to 1, and the viscosity, that's equal to 0.002. And then I'm going to change it, and then I'm going to...
The name.
Okay, I'm going to name it air. Sorry, fluid, I mean. And then I'm going to click on change and create. Yes.
And the close.
And click on inlet. Okay, the velocity magnitude, we have it as equal to 1. Okay. And then I'm going to go for operating conditions and specify that we have a gravity. Okay, the gravity acceleration in the x-axis. Okay, it's going to be 9.81. Okay.
Inlet.
Okay, and I'm gonna choose compute from the inlets. Okay, so we're gonna go to solution. We're going to go to methods to check whether it's second order or not. So it's in second order, that's good. And then we're going to go to residual. In the residual, I need to change the absolute criteria into 1e minus 0.6 for all of for the x-axis and for the x velocity and for the y velocity and for the continuity. 1e minus 0.6, also here, 1e minus 0.6. Okay. And then I'm going to go to initialization. And we're going to compute it from the inlet. Okay, initialize. And we're going to run the calculations. We're going to choose here 300 iterations in order to reach into the desired accuracy, and we're going to calculate. And as you can see, our result is converging, which indicate that our results are right. Now we're going to check the results of our effort that we did, or the problem. Okay, so here we're going to go to contours, and we're going to create the contour of the problem, and it's going to be, and we're going to choose here the velocity magnitude, and we're going to choose throughout the axis, throughout the inlet, throughout the interior surface body, throughout the outlet, and throughout the wall. And we're going to display it right now. As you can see, it's uniform. It's showing us the mesh, and it's showing us that the velocity, the velocity is increasing as we enter into the small cross-sectional area, and it decreases as we go out of the cross-sectional area, and it was at the beginning very small. And then in order for us to view the how does the velocity increase, okay, we're going to go to velocity in the XY plot, and we're going to choose it throughout the axis in order to see this in details. Save and plot. Okay, as you can see from this graph, the velocity the velocity starts to increase as we go inside the narrow part of the pipe, and it's going to reach maximum it's going to increase as the cross-sectional area decrease, and it's going to reach maximum when you reach the least cross-sectional area, and then it's going to increase again, it's going to decrease again when the cross-sectional area increases. And then right now we need to check the velocity profile. Okay, so we're going to change the axis because it's on a different axis. Okay, and we're going to to look at it at inlet and outlet. How does the velocity profile look like? So this is the solution for us. Of course, this is actually half of the velocity profile because we here consider it to be axis symmetric, so we're just displaying half of it. And this is at the inlet. At the inlet, it was not fully developed, so it had this structure. And then when it became fully developed, we had the velocity double the magnitude, double the average velocity, which is actually 1. And That's our result, and the results proves to be right because it follows the theoretical concepts.